electronically by this umbilical cord. So I'll show a few more images of this sort of landing event and the after effects of it. But this is the star of the show right here, is Perseverance. And I think that someone might have an open mic. If you could all please make sure you're muted unless you're asking questions. Thank you. So here's the view of Mars from Earth. I'm sure that you've all seen it at one point or another. Sometimes you may notice that it gets brighter and dimmer as Mars gets closer and further away from us. Or two or 3 years ago, it must have been 3 years ago now, it was as bright as I had ever seen it my entire life, because it was both at its closest approach to Earth, which is often when we launch spacecraft to Mars, but it was also experiencing a global dust storm, upping its albedo and making it this particularly bright red object. So the first aspect of the Perseverance rover mission is, of course, to hit one small target, Mars, from another small target, Earth, over a wide array of distance in between. You can also see Earth from Mars with the technology we have on the surface of Mars today. So depending on how this is coming through in the Zoom video, and if you have any flecks of dust on your screen, it's easy to miss. But this is Earth as seen by the Curiosity rover, thousands of miles away, thousands of kilometers away from the Perseverance rover in Gale Crater on Mars, which is in the same hemisphere, but almost the opposite side of the planet. So again, from this small target, we will hit this other small target, Mars, during that launch and landing process. The purpose of the Mars 2020 rover mission is multifold, but a key aspect of it is to prepare for Mars sample return. So it's the first step of this campaign to get samples back from Mars onto Earth. Mars sample return was designated in the NASA's Decadal Survey for Planetary Science as the key mission in order to enable us to fully understand the geologic processes that have operated on Mars in the past and still operate in the present, as well as to evaluate whether or not rocks on Mars preserve biosignatures, preserve fossils from ancient Martian life. So the Mars 2020 is the vehicle through which these samples are collected that will then be grabbed from the surface of Mars, loaded into a rocket, launched off of Mars, rendezvoused with an orbiter, and sent back to Earth, such that we can then analyze them with all the most advanced lab equipment that exists on Earth that is too massive to land on the surface of Mars. And to do this, Mars 2020 attempted to land in the area we thought most likely to preserve biosignatures and also allow us to collect a geologically diverse set of rocks so that we can answer many different science questions using these return samples. So we are here in this whole sample return process. We are collecting them right now. We do have samples from the surface of Mars on Earth right now, the surface and subsurface of Mars, in the form of Martian meteorites. So there are four primary classes of Martian meteorites. There are the classic ones that have been known for decades, the Shergottites, Knocklites, and Chassignites, also abbreviated as SNCs. And so these are younger volcanic lithologies. So they're either erupted out of volcanoes onto the surface as lava flows, or form and crystallize in the subsurface as intrusive igneous complexes. And these Martian meteorites are launched off of the surface of Mars by meteorite impacts. They then need to be strong, competent enough to survive the impact event itself, as well as exiting the Martian atmosphere, and then on the fortunate trajectory to be able to then fall into Earth's gravity well and eventually fall through Earth's atmosphere. They also then need to be competent enough rocks to be able to survive that journey through Earth's atmosphere and land on the ground without burning up as they enter the atmosphere. So it's a relatively limited set of rocks that we've still done some amazing science with, but because we can't really pick and choose where they come from, and because they have to inherently be hard rocks in order to be able to survive the journey from the surface of Mars to the surface of Earth, it really limits exactly the types of things that can be studied using these rock samples from Mars. More recently discovered class of Martian meteorites are these regolith breccias, which have been determined to come from the southern highlands of Mars, so this dark terrain in the image here. This is the most ancient crust on Mars that actually does not have nearly as well preserved an analog on Earth. Crust that is older than 3.5 billion years on Earth, or even older than 3 billion years on Earth, is often not nicely preserved in its pristine state because plate tectonics have mashed it up both physically and chemically. It's experienced high temperatures and alteration by water. It's experienced physical deformation by plate tectonics and burial and re-exhumation through erosion. But on Mars, because there's not plate tectonics on the planet, the ancient crust that holds information about these key planet formation processes that form the primordial crust of terrestrial planetary bodies, it's preserved there nicely. And we do have samples of this in the form of the regolith breccias. And so the value of having extraterrestrial samples that can be studied in the lab has been demonstrated both through these Martian meteorites, our current rock collection of Mars, as well as through samples from the moon, which were brought back during the Apollo missions, as well as via lunar meteorites that are ejected from the moon and land on Earth through the same process as the Martian meteorites, as well as meteorites from the asteroid belt. And so we understand that even having a small amount of material, you can learn substantially more and answer substantially more in-depth scientific questions with the samples than can be done even with the best in situ instruments put on a robotic spacecraft. So this is really the motivation to complete Mars sample return and to get these samples back to Earth, is such that we can select which samples return and select what their geologic context is, rather than just taking what we can get, finding it out in the Sahara Desert or in Antarctica, where most of these meteorites are recovered. So here is an outline of the instruments on the rover that we use to try and evaluate the geology of the landing site, which then allows us to collect the most compelling suite of samples for return to Earth. There are instruments that are remote sensing instruments like the Mastcam-Z zoomable cameras that there's 2 of them on the rover such that they can operate as eyes and also generate 3D images of the entire area that we're looking at. There's also SuperCam, which has a variety of different measurement capabilities. It can take both very high resolution images as well as perform laser-induced breakdown spectroscopy, Raman spectroscopy, and visible to near infrared spectroscopy at all sorts of distances, everything from right in front of the rover to several kilometers away. So those are the remote sensing instruments that we use mounted on top of the mast. And this rover, just to give you a sense of scale, this rover is substantially taller than I am. It's 2.1 meters tall, a little bit taller than that. 2.1 meters is about where SuperCam is located. So if you're standing next to the rover, you might be surprised at exactly how tall it is with this mast. META is the weather station that we have that records atmospheric activity, atmospheric pressure, wind speeds on Mars. There's also an experiment that I'll talk about a little bit later called MOXIE, which is a technology experiment to produce oxygen from the CO2 in the Martian atmosphere, which may be a way for astronauts and human explorers and inhabitants of Mars to generate oxygen in the future, both for breathing and water, as well as to create rocket fuel to come back to Earth. There's also a subsurface radar on this mission, RIMFAX, which is able to measure the different changes in the resistivity of the subsurface, such that we're able to map different geologic units there. Finally, on the rover arm, which is quite long and has quite an enormous mount on the front of it, we have 2 instruments to study the rocks up close, which are Pixel, an X-ray fluorescence spectrometer to get elemental chemistry, generate elemental chemistry maps at sub-millimeter scales on the surfaces of rocks, as well as Sherlock, which is a Raman spectrometer that is also particularly sensitive to organics, and again can do these very high resolution maps on the surfaces of rocks. Sherlock is accompanied by its companion Watson, which is a high resolution camera that is on the end of the arm. Then finally, the rest of the mass on this arm, which I'll show you some images of later, is the abrading and drilling system. So it's through this system that we both abrade rock surfaces in order to see the fresh, pristine surface, as well as drill into rocks to collect samples. So these are the suite of tools that we're working with, as well as the mobility tools of the rover itself, in order to determine what's going on geologically at this landing site. And here's an image of the actual rover before it was shipped off. So this is it in JPL's high bay. Just to go through a quick process of what this looks like, this is also in JPL's high bay, where you have the heat shield for landing, the sky crane unit that directed the rover to the exact location where it finally landed, and the cruise stage for the rover here. So Perseverance gets loaded up. Here's the rover itself loaded into the heat shield, which is then attached to the cruise stage here with that sky crane. The rocket pack is behind the rover in this image. So you can tell the rover's folded up. That is then covered by the actual heat shield and then loaded up into the cap of what will be the rocket to launch this off of the surface of Earth. That is then transported to the component of the rocket containing the propellant, and then it was launched on July 30th, 2020. The reason that this date was selected is because about every 20 months, Earth and Mars get to their closest approaches, where the travel time between them is minimized. So you could sort of envision perhaps in a future where we're regularly launching spacecraft to Mars, there will be a Mars season where many rocket launches occur, many more than usual going to Mars, because in that 20-month window is when the time will be minimized. And in fact, during this window, 3 different missions were launched to Mars during this closest approach that occurred last year around summertime. So just to look at the position of the planets at the time. So this was the position of Earth and Mars when the rover was launched. So you can tell that they're relatively close, but obviously Earth, as it has a closer orbit to the sun, it takes substantially less long to complete its rotation around the sun. The year on Earth is almost half of the year on Mars, a little bit more than that. But as Earth begins to catch up and then pass Mars in its orbit, and Mars 2020 kind of shoots the gap between them while holding on to the velocity it had from rotating around the sun with Earth, it eventually reached Mars when the planets were in this position here. So Earth had already passed through Mars, and about half a year had passed just over that, right? It was from June to February. And so Earth went from being on this side of the sun to the opposite side of the sun, whereas Mars went through about between a third and a quarter of its rotation and went from being on this side of the sun to this side of the sun, with the spacecraft traveling that distance in between the whole way. Then finally, we made landfall on Mars, through which there's actually a video acquired of this process that I won't go through as part of this talk, but if you have not seen it, I highly encourage you to check it out. I can provide a link as well after the talk in case any of you haven't seen it, because that goes through the whole process of parachute deployment, heat shield separation, and sky crane maneuvering Perseverance to its final spot where it was then lowered down to the ground. And then you can actually see this sky crane, this hydrazine jetpack, cut these cords that the spacecraft Perseverance is attached to, and then fly off into the distance, emerging kind of from the dust cloud that's generated by the propellant here. So to make landfall on Mars, we had to determine safe locations to land. Rather, the EDL, the entry, descent, landing engineers, had to do this. So it was determined that these black and green colored dots are all locations within this ellipse, which is the kind of 7 by 8 kilometer ellipse where we wanted to land because of the scientific value of the targets within it. These areas were deemed to be appropriate landing sites because they lacked boulders or sand dunes that would be mobility hazards for the rover if they were to land in those locations. So as you can see, the highest concentration of these landing sites is actually right here. But we ended up landing right around here in an area with a lower concentration of these safe landing sites, but it was deemed the best chance of a safe landing by the onboard equipment on the rover during the landing process, just based on the actual trajectory the rover ended up having at the end of the stage, at the end of the parachute deceleration stage. And at the very end of the landing process, we acquired an image using HiRISE, which is a high resolution camera on board the Mars Reconnaissance Orbiter of all of the different components of the landing system and where they ended up. So the parachute and back shell that initially slowed the rover down after it was sort of fireballing through the atmosphere to slow down via the heat shield, that parachute and back shell are landed over here to the left. The heat shield, after it was released such that the equipment on the rover could begin monitoring and localizing where it was approaching near the surface, that landed off to the east of Perseverance, over here in the right of the image. Perseverance itself landed in this area, and you can sort of see the butterfly wings here of the propellant from the descent stage from Sky Crane, clearing off dust from the area right around where Perseverance was lowered. And then the descent stage landed here after flying off from dropping Perseverance off such that it would crash land a safe distance away from the rover itself. And so here's zoomed in, colorized images there. You can even see the stripes on the parachute in this high resolution image. And we actually captured when the rover landed on the surface with our rear HAZ cam, our rear hazard camera that's on the bottom of the rover and kind of looks backwards. We captured the plume from the descent stage crashing. So now we were in Jezero Crater. This is the first image that was acquired from the front HAZ cam upon landing. So you can see the rover's shadow. You can see that we're in a very flat area, right? And that was by design because that made it a safe landing site. So now, why do we decide on going to Jezero Crater? Here's where much of the actual science comes in. Earth and Mars are obviously very different right now at this stage in their history after they've existed for many billions of years. Earth, as we're all familiar with, has abundant water and a thick atmosphere, a hydrologic cycle that, along with photons from the sun that are used by plants to conduct photosynthesis, a hydrologic cycle that, along with those photons from the sun, drives a very rich organic carbon cycle through which we derive all of our energy largely. There are also systems on Earth that obtain their energy from water rock reactions, like hemolithotrophic systems that are at the bottom of the seafloor or in the deep subsurface of Earth's crust. Mars is lacking that rich organic carbon cycle, that thick atmosphere, and that abundant water on its surface. It's a pretty dry and desolate place, at least on its surface. And so what we're interested in is looking back at an era of Mars where it likely had, for at least certain time periods, billions of years ago, periods where there was water on the surface. We see evidence for lakes that existed on ancient Mars. We see river channels that are still carved into the crust and preserved there today. And the rocks in Jezero Crater hold that information about this stage of Mars billions of years ago. And so investigating those rocks will tell us about what the actual conditions were like. Was it very, very cold when this water flowed on the surface, just above the temperature where that liquid water could form? Or was it warmer climate at the time, at least for some transient periods when those lakes formed? What is the nature of water and rock interacting, and were habitable environments generated during that time? And so here's just a visualization from NASA's scientific visualization studio of Mars going through this process of having, for some periods in its past, this sort of surface water environment, and then being cleared out to the planet we're familiar with today that still has some channels and evidence of surface water preserved, but is largely cold and dry. Here's a topographic map of Mars, and I'll show you here where Jezero crater is located. But just to give you some orientation, the blues are the lower topographic colors, while the reds and the whites are the higher topographic colors. So here, the most prominent feature to my eye when I see this are the Tharsis Montes. So this is the Tharsis bulge here. And so this is a major volcanic complex that hosts Olympus Mons, as well as the Tharsis Montes here, and Valles Marineris on its side. So this is a large, relatively geologically young volcanic bulge here. And there's another major volcanic province called Elysium Mons over on the right-hand side of this image here. So those are relatively recent volcanics. The area here towards the south that is covered with impact craters, this is that ancient Noachian age crust in the southern highlands that I was talking about previously. So this is the really ancient crust where there's no good analog for it on Earth that hasn't been affected strongly by plate tectonics. And then here in blue is the northern lowlands. So it's a topographic dichotomy where the southern highlands are topographically much higher than these northern lowlands here. So Jezero crater is near the boundary of these southern highlands and northern lowlands. It's right where this arrow is localizing. So it's in this what's called the Nili Fosse region, just north of Syrtis Major, which is this volcano right here, and just to the kind of west-northwest of the Isidis Impact Basin, which is this large, round, lower topographic area here. And this is what Jezero looks like from orbit. So this is using the cameras on board the Mars Reconnaissance Orbiter to image it. So you can see that there's a channel, an ancient river flowing into this crater from the west, as well as another channel flowing into it from the north. And there's actually a channel that we determined is flowing out of it, coming out here from the east. So because there are two river channels flowing in and a river channel flowing out from the east, you can estimate what the lake level had to have been in order for it to have been full enough to have that river channel flowing out from the east. So it's based on this evidence, as well as the presence of a delta in the lake, that we're quite sure Jezero crater hosted a lake during its past. And the crater itself is formed by meteorite impact. So that's what made it a basin in the first place. So now we're going to zoom in around this box here. And here we've mapped out some of the key geologic units. So just to give you some orientation, here is where we landed. So that's what I was showing you before to localize our landing site. So here's the river channel feeding into the western part of the crater. At the end of the channel, there's this delta that's outlined in blue. There's also this material that's olivine rich. Olivine is a volcanic mineral on Earth that are outlined in red here, as well as a possible northern delta at the edge of the northern channel outlined in yellow here. And so you can see just by a direct comparison with deltas on Earth. So here's the Nile River's delta, flipped from the Nile River delta is the Nile River runs more south to north, but I flipped it here to be west to east just so that the orientations line up. So here's the Jezero Delta compared to the Nile Delta. You can see that they have those same characteristic deltaic geometries. They're at the end of a river where that moving river water full of sediment hits standing water such that the sediment load drops out. But a key difference that you can see is that the Nile River's delta is substantially larger than Jezero's. So here's a 160 kilometer scale bar compared to a 9 kilometer scale bar. This is just a testament to, even in this environment on Mars that was selected because of its clear evidence for past surface water, the level of surface water is still much, much lower than modern day Earth. Just because Earth is a planet that's driven by water, whereas Mars sort of seems to have in the past have been driven by water and surface water processes, but not to the extent that Earth is today. Otherwise, you'd expect much geologically larger features comparable to the Nile River. So here's a visualization of what you could expect Lake Jezero to have looked like, with channels flowing into it and out of it billions of years ago. And the most exciting thing we could envision possibly finding on this mission is something like this. So if this doesn't look exciting to you, let me explain to you why it's exciting. So these are modern day stromatolites, which are formed by microbial activity to precipitate out these solid phases and form these kind of rock-like structures with very characteristic textures that allows them to be analyzed as biosignatures even when they're extremely ancient. So for example, here are some ancient stromatolites, more than 3 billion years old, that are in the Pilbara region in Western Australia. And so you can see these sort of characteristic textures where the microorganisms are kind of building out these structures that allow us to effectively look at a macro scale texture and evaluate it as likely not caused by abiotic processes. Now, this is very exciting because if the rover were able to see something like this, then we would attempt to collect a sample of it. And while we could potentially have a strong feeling that there might be biosignatures in this rock, while just through the rover investigation on the surface, there would then be the potential for this sample to come back to Earth and be analyzed in the lab for things like molecular biosignatures, isotopic biosignatures, to go along with this in situ data of morphological biosignatures. River deltas are also habitable environments, and the delta that I showed you before in Jezero is another place that we are planning on looking for biosignatures, since deltaic environments preserve biosignatures very well on Earth. Now we're at the point of being able to analyze the delta from the ground, where so this image on the right here is acquired of this area of the Jezero Delta too. So we call this the Kodiak remnant. So this was once part of a larger delta, but erosion has moved most of the delta back, and this is a remnant that still remains there. And we're actually now able to image it with the rover and see what the kind of fine scale structures in the delta look like. We're also able to look at the delta front from very far away. So you can see the image I'm about to show you was captured from right here, right by the landing site. Here's a 400-meter scale bar, and here's the field of view of the image. So we're looking right at the scarp on the delta front. And we're able to see both a lot of talus, a lot of rockfall, but also some kind of primary structures containing bedrock here. These beautiful bedrock exposures that have really distinct, sedimentary facies in them, sedimentary structures that can be used to evaluate what the processes that deposited these rocks were. So, and here is a high resolution image of that delta front. And here's a version of it where it's annotated to show these different types of sedimentary structures, where we see cross-bedding, where we see layers that are not planar, but are rather tilted and curved in their orientations relative to other layers in the delta, as well as relative to final scale bedded layers here. So these are characteristic sedimentary structures that are observed on Earth that are now seen on Mars, as well as conglomerates with larger rocks in them that then need to be formed by higher energy, faster flowing surface waters to be able to carry those larger rock loads in that surface water as it flows into Jezero crater and then is deposited out, right? As the water begins to not flow fast enough to then hold on to those larger rocks anymore, the rocks fall out and form this conglomerate. So we're actually able to now analyze this delta from the ground. There are multiple different geologic units in Jezero crater, and we plan on sampling a wide variety of them. So we landed on this crater floor fractured rough unit, which is labeled in tan here. And we're planning on collecting a sample of that, and in fact already have. And then there's this dark green outline, which is called the crater floor fractured 1 unit. And this large kind of feature here that almost looks like a hand with a mitten on it is called Seta. And this Seta feature is something that we're also interested in collecting a sample in. at some time during the mission. It is difficult to traverse through Seta. It's covered in sand and dunes. And so instead of traversing through it, we're going to drive around it, eventually getting to the delta front to be able to then analyze the delta, analyze this unit up here, the margin fractured unit, and then eventually reach the crater rim. So as I said about the traversability in Seta, here's an image from the helicopter, which I'll talk about a little more later, that shows that the traversability potential of Seta is quite limited. So again, this is this dark green area over here, where it's actually flying specifically over this section of it here near the rover, where it's just covered in these dunes that would have high potential for the rover to get stuck. So, but Seta itself shows some intriguing geologic variability. So we actually have observed both from far away and up close these layered rocks within Seta. Geologists get very excited about layered rocks because they can often indicate what the type of deposition of those rocks were, and then that coupled with up close investigation, you can determine if these rocks are deposited in more of a sedimentary environment or by more volcanic processes. That obviously dictates their potential to be habitable and to host biosignatures. And so the fact that we're seeing these layered rocks in Seta is intriguing because it leaves open the possibility of a sedimentary origin for these rocks that we can test against the volcanic hypothesis as we get up closer and can look at it with the higher precision instruments that are on the arm of the rover itself. And just to give some orientation here, so we're down over in this area of the Seta thumb of the mitten. So now that this is where the rover is traversed along the thumb here, and I'll show you an image just taken from this blue dot with a field of view and a view shed outlined in the blue here. And it's showing our search for a first sampling site. And so we took this Mastcam Z image here, and here circled is a general area of the rocks that we then drove the rover to try and collect these first samples. So here is an image of the rocks that the first sample was collected from. Then we started finally employing this drill and abrasion tool that is on the rover. So just like drills that you have and use in your home for personal construction projects and what have you, there are multiple different types of bits that can be put into this drilling system that's on board the rover. There are both abrading bits that just scrape off that surface of the rock that, as you can tell from these images, is sort of homogeneous. It makes it relatively difficult to interpret what type of rock lies underneath these surface coatings that have formed over billions of years of weathering in the modern day Martian environment. These types of coatings make it much harder to figure out what the actual lithology, what the rock type is that's underneath them. And so these abrading bits allow us to, in certain locations, remove that and then study the rock more in depth up close. So I'll show you an abrasion patch shortly. Then finally, when we decide to collect cores, we use these coring bits here. And so they drill into the rock, and then this coring bit leaves the rock with a sample of the rock in it that's about the size of a finger. And then there's also a regolith bit that can be used to collect kind of the sandy, loose, unconsolidated material that's on the surface. And here's just a video of some of the arm mobility tests. You can see some of the different axes of movement that the arm has itself. So it can kind of spin around that drill and instrument containing component of it, while also moving something similar to a shoulder joint and something similar to an elbow joint in order to kind of access at the right angle these rocks that it's studying and or drilling and abrading. And here's an image of the abrading bit when we first loaded it into the drill on Mars, and just an image from another view. So you can imagine that having this abrade your arm would not be a pleasant experience. That's why it's good for removing the top parts of rocks. And then these sort of rough textured components of the arm are used to mount the arm on top of the rock surface such that it stabilizes the drilling system and abrading system itself. So here's an image of our first abraded rock patch here. And you can see in it that there's these sort of white components of it, as well as these red components and darker components. And so using the instruments on board the rover, we analyzed this patch and determined that this would be a good location to sample. So then this is an image of kind of getting an up close look with the arm instruments at these types of rocks. And then from that, we decided, okay, this is a good sample to drill. So we took out the drilling bit, which you can see here, and then went and took a borehole here. So here's that abraded patch that I just showed you, the rover looking down on it, looming over. And then here's the borehole from which that first sample collect attempt was attempted. But we got a surprise that the sample tube actually ended up being empty. And so by realizing that the sample tube was empty, kind of looking around us and realizing that we didn't see the core anywhere, and then looking at the size of this tailings pile that was around the borehole, we realized it's likely that this sample disintegrated during the drilling process itself. And that's why instead now we have an atmospheric sample rather than a rock sample collected in this tube, because the rock sample itself was destroyed during the sampling process. So this is a sign that this rock has interacted with water to a substantial extent, even a substantial extent to the point where it was so fragile that it couldn't survive the drilling process. So following that, we then went, okay, yeah, and so you can see again around this borehole, this is a Watson image, so the camera that's on the rover arm looking down into the borehole itself, you can see the nub of the core that was taken out, as well as just kind of a pile of loose unconsolidated material around the hole, as well as unconsolidated material that kind of coats the interior of the borehole just as part of the drilling process. So it kind of hides what the primary rock textures are on these borehole walls. So we were able to see that these are actually the disintegrated remains of the core probably around this borehole. So then we decided to move on from this area where we were just at, so where my mouse cursor is circling, and then traverse along to this ridge to this area up here. And we call this sampling site 2 the Citadel, where we decided to attempt to collect another sample. So now this is the rock that we decided looked like the best target to maximize the chances of collecting a scientifically compelling sample. This rock is called Rochette. So we abraded the patch, we abraded this rock. And you can see this abrasion patch, if you just kind of compare it to the other abrasion patch, in your mind's eye, it has more of these linear features that are imparted onto it from the actual abrading bit itself. The kind of rock walls are more vertical, and these differences between the abrasion patches implied that this rock likely was more competent, likely had a better chance of surviving the drilling process compared to its cousin that we tried to drill earlier in the mission that disintegrated. So then finally we collected we drilled into this rock again. So this is actually the abrasion patch that I just showed. This abrasion patch was right down here, and then during the coring process it got covered by the tailings. Since this rock is kind of sloping down towards us, we cored it again, and this time it was a success. We had a rock core in the sample tube that is now ingested into the rover's sample collection unit, which is here's a video of it during some of the testing while it was on Earth. So here, this is the sample tube here containing the rock core, and this unit with all the different holes on it is the sample collection device for the rover itself, where the samples are then stored and placed by the arm. So we now successfully have a sample in the Perseverance rover. So at that point, or at this point, I think it would be a good time to take some of the questions on the sample return aspects and some of the geology, science of Jezero crater. And I have a few slides about how the Perseverance rover mission is also helping pave the way for human exploration that we can get into after that. So we could take a few questions at this time before going into these next slides, if there are questions.
Okay, Jonah.
Yes, I have just one main question, which is how do you account for the contamination that is coming from the rover itself when you do these kind of abrasions or drillings or all these kind of studies?
Yeah, it's a great question, and something that the return sample scientists and the rover engineers have thought a lot about. So we have witness tubes that are meant to be returned to Earth as blanks, and so they've gone through the whole process that all of the other sample tubes have as well. And then will be stored in the rover unit along with the rest of the sample tubes, but they don't have any rocks within them. So the plan is that those blanks will give a sense of what the contamination was as the rover left Earth's atmosphere, traveled through space, went through this pretty violent process of entry, descent, and landing, and then also has experienced the Martian surface environment and abrasion and drilling for the same amount of time as these other samples. So that's the way it's done, is with witness tubes. In terms of actual rover material getting in the tubes itself, with some of the instruments that you expect these samples to be analyzed with, it could be relatively easy to differentiate some of the artificial materials of the rover from the more natural materials, just in terms of their composition and texture. So there's a few different avenues to do that contamination test, but those are the primary ones that are being employed by the mission.
Thanks.
Thank you.
Jürgen?
Yeah, so the first sample crumbled and you couldn't take it aboard. Would it have been interesting and you just had no means of collecting it, or are these soft samples inherently much less interesting than hard rocks?
Well, so the soft samples are quite interesting, and there's multiple different types of soft samples. So there's some soft samples that would probably hold together relatively well and kind of clump together into the core itself. So you could envision something like a mudstone doing that, and we'd still be able to extract it. This one was interesting because it seems like with the way it crumbled, there were a lot of different grains in it that were kind of held together by this really weakly cementing material, and that it was kind of that the grains had no way of clumping together or coheating to each other in any way to be able to stay in the sample tube itself. So this is kind of, there's soft rocks and then there's soft rocks. You know, there's multiple types of soft rocks. Some can be collected by the sampling system. Some, like this first attempt, could not. But it really depends on more fine scale properties of the rocks themselves. Soft rocks are quite interesting though, because for example, mudstones on Earth are really, really excellent at preserving biosignatures. If you get soft, fine-grained sediment, you can envision a larger scale fossil. It's sort of easier to envision, something like a leaf or a bone or a fish, small animal, getting buried in with this mud. And then as that mud is turned to rock, is lithified by other fluids, because it's so soft, the biosignatures kind of stay within there and are not destroyed by the rock process, the rock forming process itself, or the sedimentary deposition process itself. So those would be targets that we're really interested in to look for their biosignature preservation potential on Mars, because even though they're soft, they are quite interesting. So you know, we're hoping to encounter some relatively soft rocks and also be able to drill them because of their more fine scale geotechnical properties that are different from this specific rock sample that crumbled as we were sampling it. Great question.
Okay, thank you. Next one is Ashutosh.
Hi, two unrelated questions. One is, what is the sort of decontamination procedure to make sure that the rover doesn't carry Earth viruses, bacteria, whatever, to Mars? And second, what is the power source of the rover?
Cool, great question. So yeah, the planetary protection requirements for the rover are quite intensive, as they should be, because we don't want to forward contaminate anything from Earth to Mars. So there's a variety of decontamination processes. I'm not entirely familiar with all of them, but some of them include using UV light to sterilize and high temperatures to sterilize the equipment before it's loaded up into the spacecraft itself. And there are a variety of other decontamination processes that each of the different components of the rover undergoes to the extent that they're capable of doing it, right? The electronic systems may be too sensitive to certain types of decontamination processes, such that they cannot be put through quite as extensive decontamination as some of the components of the rover that do not contain electronics. But yeah, high temperatures, UV exposure, those are a couple ways to decontaminate. And there's a variety of additional ones that I'm just not cognizant of, that there's way more intelligent people at NASA working on to get these spacecraft sufficiently decontaminated to send to planetary surface environments. And just as an aside, that's a very important question that I think will become increasingly important as NASA continues to push the boundaries of sending robots to planetary environments that have a strong chance of being habitable or preserving extant life, existing organisms, or maybe dormant organisms in the future. So for this, you could envision perhaps the deep subsurface of Mars being one of these environments where conditions are still enough that you could expect, or are still habitable or protected from radiation enough that you could expect perhaps preservation in ice or in fluid of live cellular tissues, or live cellular structures rather. The idea is that forward contamination in those environments is an even bigger problem, because you could potentially see, maybe even on icy moons out like Europa and Enceladus, a situation where an Earth organism could actually get started in one of those environments if somehow that robotic spacecraft accessed a habitable environment. On the surface of Mars, there's really no way that Earth-like life could propagate. The surface of Mars is just not habitable. It's much too dry. The temperature variations are too intense. The radiation environment is largely the most deleterious variable for life on Earth. And the desiccation is also the very low water activity, very low humidity. That combination of factors makes it such that even though we decontaminate the rover before going to Mars, there's really no way for Earth-like life to survive for long periods of time on the surface here. So that's the answer to your first question. The second answer, this rover is nuclear powered, and the Curiosity rover is as well. So the Curiosity rover was actually able to, during the last Martian dust storm, continue to perform some rover operations, even though it was difficult to see because there was dust everywhere, but it wasn't relying on solar power to power all of its instruments like many other spacecraft do, such as the Mars exploration rovers Spirit and Opportunity were solar powered, and InSight, the seismometer that's in the northern lowlands of Mars right now, is also solar powered. But yeah, this rover is nuclear powered.
Thank you. Wonderful.
Thank you.
Okay, thank you. There were a few more questions in the chat, but I think it's better now to proceed with the talk in order not to interrupt the flow, and I will address them later.
Yeah, sounds great. Yeah, and I think that the timing will work out nicely with the few slides I have left. So for this next part of the talk, before we go into the full Q&A session, I want to talk about how the equipment on board the rover, the technologies, is really paving the path for human exploration of Mars. So this GIF that has been left up during the time we were fielding these few questions is a selfie taken by Watson on the rover's arm of the rover itself, and also the Ingenuity helicopter that came along for the ride with Mars 2020 to the surface of Mars. So we see the rover looking at the camera and also looking at the Ingenuity helicopter itself. So here's a video of Ingenuity, which is a mobile Martian scout. It has much better mobility than the rover does, because it doesn't have these constraints of needing to really worry about flying over dunes the way the rover can't drive over dunes, or flying over big bouldery fields that the rover would have more difficult time navigating. It can lift up and fly over, and it just needs to find a safe place to land and to take off, and be able to kind of have a sense of what the ground is like beneath it. So Ingenuity was located on the rover's belly as it was sent to Mars. So you can actually see it here is folded up onto the rover itself. So it's only a few pounds, couple kilograms, very lightweight, so that it can fly in the low density Martian atmosphere. So here it is loaded up on the folded up rover before the heat shield is placed covering this entire package to be sent to Mars. Then once we got onto the surface of Mars, we lowered it down and then dropped it off onto the surface. So here's a video of it going from that kind of folded position on the belly to having its legs down, to then being fully separated from the rover. And then the rover then backed away so that Ingenuity could, have the sun shine on its solar panels and prepare for its tests to fly. So after we dropped it off, there was some rotor blade testing where we tested to make sure that the rotor blades were working properly, and then flight. And so here's an image on the left taken during Ingenuity's flight. And then on the right is a series of images stitched together showing the takeoff process and the flight process. And I like this one because you can see the rover tracks in it, which gives you a sense of scale. So, about a meter separation or so between those rover tracks there. This Ingenuity helicopter is about 10 meters off the surface flying over, and it's now flying over terrain that, or it's about to fly over terrain, it's thinking about it right now, that we would never fly or never drive over for the most part with the rover, these kinds of dune fields that would make it easy for the rover wheels to slip and get stuck. So now this Ingenuity helicopter is a mobile scout that's being employed by the mission to look at areas that are far away from the rover to see if they seem scientifically compelling enough for us to take the more time-intensive journey to get the rover there. So you could also envision future human explorers on Mars whose mobility will be constrained. I mean, if you've walked through sand dunes, up and over them, over and over and over, you're familiar with the slippage of the sand, making that process quite difficult. If you're trying to conserve oxygen and resources and water, having these sort of lightweight mobility scouts to scout out areas that are either scientifically interesting if you're on more of a science-oriented campaign, or scout out areas with water-rich minerals if you're looking to extract water from those types of resources. That is a key technology that's now been demonstrated on Mars that human explorers can use to maximize their efficiency while on the surface. And so, yeah, it covers and maps difficult terrain. Sorry if any of you get motion sickness from this. If you do, just look away. But here's another video of the helicopter flying over the surface. And I believe this is the one where you can actually see it land. It might come up pretty abruptly here. Oh, there we go. It just landed. Now it's looping again. So you could imagine also a much larger one of these helicopters having scientific instruments on it like Perseverance does, and also being able to carry out a more mobile, kind of large-scale robotic space exploration mission. So here's an example of a site that we saw with Ingenuity from the air that we were considering driving the rover towards, that we were then able to look at it more closely and realize that it might not be worth the rover's time to drive to. So this really is a totally new type of exploration, using more mobile scout helicopters in order to determine where the larger and harder to move rover should go to use its more intensive scientific instruments to study the rocks. And so that's really a way that we're maximizing science return through the partnership, the teamwork of Ingenuity and Perseverance. And here's another video acquired during a flight showing some interesting terrain from the sky. And I had to throw this in there. So here's an image of Perseverance by Ingenuity during one of its flights, right off in the corner there. So they hang near each other so that the helicopter can send Perseverance some of its information. So, and then here's a photo of Ingenuity from Perseverance itself with kind of the hills and the crater rim of Jezero in the background. So like I said, these types of Martian helicopters, they will be key in future human exploration of Mars, and also enable potentially robotic exploration missions that use the sky to get around rather than using the ground, and therefore have much better mobility. As well as perhaps the potential to explore areas like caves that you can traverse on the ground, but perhaps through the sky is an easier way to do this. So the Ingenuity technology demonstration and the awesome team that made it happen is a key aspect of how the Perseverance rover mission is also looking forward to enabling human exploration on Mars. Another way that this mission is looking towards human exploration is through this instrument MOXIE, which stands for the Mars Oxygen In Situ Resource Utilization Experiment, that makes oxygen from the carbon dioxide in the Martian atmosphere. And the MOXIE team that put this together has performed tests on the surface of Mars to make oxygen directly out of the atmospheric CO2. So here's kind of a breakdown of the compressors and the systems within the MOXIE unit itself. It takes in the atmosphere and compresses it, and then turns it into oxygen and senses how much of that oxygen has successfully been created. So the MOXIE instrument here is a key technology demonstration of how we can take CO2 from the Martian atmosphere and turn it into oxygen. Now, finally, another aspect of Mars that humans will need to deal with once they get there is the dust. There's dust everywhere on Mars. This is an image of the Curiosity rover, which has been on the surface since 2012. And you can tell it's gotten very caked in dust during that time. It's lived through a dust storm, been covered by dust then. And this dust is sub-micron in some of its smallest grains are smaller than a micron. And you can envision that really messing with electronics, with equipment, and potentially having impacts for human health as well. So really understanding this dust and its cycling is also key to enabling human exploration on Mars. And so Perseverance, through both the Meta weather station and atmospheric observatory on the rover, as well as through videos just sort of studying the way dust moves across the landscape and is lofted into the atmosphere and how that correlates with different changes in atmospheric pressure, Perseverance can kind of study that dust cycling on Mars, which is largely what controls the weather on Mars, and will have impacts for human exploration, like when some equipment should be moved and protected from the dust, and when a dust storm may or may not be coming in, such that how that will interfere with human exploration operations can be accounted for as far ahead as possible. So just finally to end, here's a Martian sunset captured by Perseverance's cousin Curiosity on the other side of the planet. Another thing that humans will need to learn how to deal with on Mars isn't just all these types of variables of scouting helicopters, creating oxygen, and dealing with dust. There will be some things that are very not Earth-like the blue sunsets that are on Mars. Obviously on Earth, we have red sunsets and blue skies. On Mars, it's the opposite. You have a red sky and a blue sunset. So those will be the things that these missions prepare us for through these images, but that we really need human eyes there to fully appreciate. So just to sum up the science highlights here of the mission thus far, and our first 200 sols, our first 200 Martian days, before I wrap up here. We collected the first rock and first atmospheric samples for return to Earth. We confirmed that there was a paleolacustrine and ancient lake environment in Jezero crater by imaging the deltas from far away. characterized multiple different deltaic units using the cameras on board the rover mission, constrained how those units were deposited in different water-rich environments on Mars. We investigated multiple units on the crater floor, both SETA and the crater floor fractured rough unit. And we made observations to constrain the Martian dust cycling and weather patterns, which will have key implications for understanding current processes on Mars and how that feeds forward for human and robotic exploration. Some of the exploration highlights are the first flight by an aircraft off of Earth, and that unlocks these new strategies for both robotic and human exploration missions as scout reconnaissance vehicles on both large and small scales. It was the first in-situ production of oxygen from the Martian atmosphere, and the first footage captured of landing on Mars, which again, I encourage you to check out on your own time. And then there were multiple records set for autonomous navigation, driving distances, as well as characterization of these seasonal dust cycling, dust devil activity, which affects solar panel energy production, as well as a variety of factors relevant to human exploration. So with that, I will take your questions for the next 25 minutes or so. And I thank you very much for your attentions and the questions that we've gotten so far.
Thank you, Jesse, for this fantastic talk on this absolutely fascinating subject. Now we have a few questions piling up in the chat. I will read them afterwards. Let's start here with the raised hands. John.
Well, thank you very much for a wonderful talk, Jesse. That was quite amazing. My question is, you talk about the various hazards that humans will have to deal with, but you haven't mentioned radiation. And that, it seems to me, is quite a problem. How do we deal with that?
Yeah, that's a good question. There are many people at Johnson Space Center also working on this question of how humans deal with radiation in planetary environments, and effectively building structures to try and protect from the radiation is the most obvious way to do it, right? In the short term, is to have your habitat have some way of protecting from radiation, either by kind of being covered by water or radiation absorbing materials. So that's one way to curb it. But they're sort of like on the International Space Station, you can apply these methods to kind of mitigate the radiation, but it will generally be more intensive than it is on Earth. And perhaps a longer term solution, once humans get a better foothold on Mars in terms of inhabiting it, a more long-term solution may be to inhabit subsurface environments. There are extensive cave networks in the younger terrains of Mars, the Amazonian terrains, that are formed as lava tubes, and lava tubes are formed during the Pohoihoi lava flow process, and the lava solidifies around this tube, forming rock, but then molten lava continues to flow through the lava tube, and eventually, as that lava all exits, it forms these kind of long snake-like interconnected, sometimes cave networks. And it could be a better long-term solution than to inhabit those subterranean environments, because it really only takes a couple meters of rock to protect you substantially from radiation and lower the negative impact that it has on human health. And if the more rock you get between you and the radiation, the better. So those are kind of the short-term solutions. Probably has to do with the habitat, and the long-term solution probably has to do with where we end up, where humans end up living, the highest concentration of human on Mars, and perhaps a subterranean environment will be a better place to do that.
What about on the flights? What about on the flights, to and from Mars?
Oh yeah, well, that's sort of the types of issues they're working on the ISS, right? Is how do humans respond to those high levels of radiation during space flight for long periods of time. So for example, Scott Kelly, right, has spent a year up on the International Space Station receiving those similar radiation doses as to what would be experienced on an interplanetary voyage. And they're actively studying what the effects have been on his health. So for that radiation question, the whatever organization is sending humans to Mars will do everything they can to mitigate it. But one of the things NASA is doing is also just trying to understand what the actual effects of it are on the human body in the long term, and whether or not it's then safe to send humans and expose them to kind of the raw levels of radiation, or what the level they need to minimize it down to is for the actual mission to be safe. Another factor is Mars has a crustal magnetic field, so Earth radiation from the sun is largely mitigated in Earth's environment by being captured by Earth's magnetic field, and then a lot of that those particles interact with the atmosphere to form the northern lights, right, where the poles of Earth's magnetic field have those charged particles kind of falling into the atmosphere. Mars has not a global magnetic field the way Earth does, but rather small localized crustal magnetic fields. But the strength of those local magnetic fields actually varies by orders of magnitude. And so another possible decision they can factor in where to land humans on Mars might be where this relatively, in terms of Mars magnetic field strength terms, this relatively strong magnetic field exists, which might mitigate a little bit more of that radiation. Yeah, thanks for the question.
Okay, thank you. Gilvan.
Hi, thank you for the excellent talk. On this MOX experiment, wouldn't be much more efficient to take the, I mean, we will need the water anyways if we're going to colonize Mars, so it wouldn't be any efficient to take water and to make oxygen, then they can use it to burn the hydrogen and make fuel or something like that.
Yeah, that is definitely another way to get oxygen and hydrogen and water. And so there are also NASA projects that are or NASA funded projects that are oriented towards characterizing what the water resources on Mars are, from where the ice is underground to where the hydrated minerals are that contain water and they're kind of solid solution structures, to the water content in Mars regolith. The Mars regolith, that kind of unconsolidated material on the planet, contains about 3 to 4 weight% water. But sort of like on Earth, how there's multiple different ways that we humans get water, right? We get it from aquifers, as well as from freshwater sources like rivers, as well as some people who live in wetter environments get it from kind of rain catchment systems. It's probably a good idea to have multiple ways of getting oxygen out of the resources available on Mars, such that if there's an issue with one of the ways, you have dissimilar redundancies in your system, such that an error or a technical fault requiring repairs in one type of system, you're then able to lean more into another system, like, for example, collecting the oxygen straight from the atmosphere, such that your risk is mitigated to the greatest extent possible by dissimilar redundancies. So, I think that definitely going after the actual water that's in the Martian crust is a good idea from the human exploration perspective, but having this MOXIE technology is also key to making sure we have a diverse set of ways to collect those resources that are dissimilar.
Thank you.
Okay,
Thank you.
Next one is Sartak.
Yeah, hello. Thank you for this. So my question was that what ruled out the polar caps as a possible site for excavation? As we see on Earth polar, we see the preservation of bacteria and viruses pretty good. So what ruled out for the Mars?
Well, so for this specific rover mission, one of the issues is that it's much more difficult to land on the poles. So usually it's substantially easier to land at both lower elevations and at kind of the mid latitudes due to some orbital dynamic considerations that are taken care of by other engineers at NASA. And so part of it is just the difficulty of landing. But if you also consider the kind of objectives of this mission. It's both to look for biosignatures, but it's also to collect a diverse suite of rock samples. And if you were to land just on an ice cap, you could collect a bunch of ice samples, but it wouldn't really necessarily be a diverse suite, right? And it would also be kind of difficult to localize what areas would be more and less likely to contain some sort of biosignature, compared to with rocks, we're able to study the rocks, study the lithology, the composition, the chemistry of the rocks, the facies, and compare them to rocks on Earth to try and figure out what the environment those rocks were deposited in was like. And some of those environments are more and less habitable. So through that, we're sort of able to read the rock record to localize where to collect samples, which really helps with the strategic exploration component of the mission and developing and maximizing that. So I'm sure that there will be missions one day in the future that go to the pole of Mars, and they did attempt to land on the pole of Mars many years ago, and it was unsuccessful, unfortunately. But eventually the poles of Mars will be explored, much like the rest of the surface of Mars, and it will be interesting to see what we find there.
Thanks.
So thank you for your question.
Thank you. And next one is Robin. You must unmute yourself.
You can still not hear me, or
It's not loud enough.
is this any better?
You must turn up the volume.
Yeah, I can't hear.
You must come closer. It's not to understand.
Is this any better, or is it the same?
A bit.
Yeah, I can hear you now.
Sorry about that. Is there any? I was wondering if there's any worry about the nuclear energy source affecting the experiments on the one hand, and my other question was, is there any seismic activity of concern, like significant seismic activity for the rover or for the experiment or the samples?
Yeah, good question. One thing that's the nuclear powered tail, it generates a lot of heat relative to other areas on Mars. So if the rover sits in an area for a long period of time, it sort of becomes kind of the warmest area on Mars, other than maybe if Curiosity has been sitting there for a long time in its area, since it's also nuclear powered. But that can largely be leveraged in more positive than negative ways in terms of looking at how the rocks respond to that change, because the heat itself is, as long as you can account for it and acknowledge that it's happening, is relatively easy to account for at the levels that the RTGs or that the nuclear powered devices heat levels are at. So it's not really an issue for the experiments. The landing system, the heat from the landing system is actually probably substantially hotter than the heat from the power source. And so it's nice that we're now far away from the landing site where those propellant rockets were burning hot down relatively close to the ground. Now we're sort of further away from that, which makes us confident that we're not contaminated by that heat source in any way. And your second part of your question was, sorry, can you remind me the second part of your question, please?
On the seismic activity on Mars.
Right. Seismic activity. So there is seismic activity on Mars, and that's been demonstrated by InSight, which is a separate NASA mission that landed in the northern lowlands. So it's kind of let's see, I'll pull up the map. Here we go. So yeah, the InSight mission is more like in this northern lowlands area here, and it has detected seismic activity. It's lower levels of seismic activity than on Earth. So the magnitudes are more like in the 3 to 4 range. Last I checked, maybe they measured some that are higher than that at this point now, but it's really not what you envision with like the really strong shaking, damaging earthquakes on Earth. And so while there is probably some seismic activity on Mars, the rover doesn't really notice it. You kind of need to be looking. You need to have an actual seismometer like InSight has on the surface to be able to measure and notice that seismic activity. You have to kind of be actively looking for it, because we've had rovers on Mars like Opportunity and Spirit. Opportunity's mission, I think, lasted for a total of almost 15 years, and it wasn't really interfered with by seismic activity. And Curiosity has been there since 2012, and seismic activity hasn't noticeably interfered with it either. So while that seismic activity is interesting, because in missions like InSight, it allows us to measure the properties of the crust and the mantle and the core of Mars, much like seismic studies do on Earth, they're not really hazardous for the rover. But yeah, it's a good thought.
Okay, thank you. It's exciting to hear about the progress. So thanks.
Okay, next one is
Thank you.
Okay, next one is Maximilian.
Okay, hello. My question is, how is Ingenuity controlled? Do you give it a very specific set of commands, like go up to meters, turn right 90 degrees, etc., or do you just give it a path to follow, or do you use a different way of controlling it?
Well, it's a mixture of both kind of manual and autonomous choices. Like there's definitely a lot of human considerations that go into whether an area is safe to fly over or not. But because of the time delay between Earth and Mars, there's a lot of autonomy that's kind of necessitated in many of the robotic operations, because it takes about 7 minutes to get a signal one way from Earth to Mars. And so you can't directly pilot any of these things, but you can sort of make decisions about what they are asked to do. Is the kind of general way that both Ingenuity and Perseverance are operated.
Okay, thank you.
Yeah, thank you.
Thomas?
Well, if it's me, Thomas, then I can ask the question now. It goes back to the beginning of your talk when you talked of the meteorites from Mars. And I was just wondering how you know that they do originate from Mars. With what method do you determine that? Yeah, those things.
Yeah. So the original way that it was determined was because the composition of noble gases in the Martian meteorites, I think this was first demonstrated, I might be wrong about this, but I think it was first demonstrated with ALH 84001, which is actually an orthoperoxenite that is sort of a unique Martian meteorite. The noble gas composition in that meteorite exactly matched the noble gas composition that was measured for the Martian atmosphere by the Viking missions. And so that exact match is what the first and strongest piece of evidence that these rocks were from Mars.
Okay, fair enough. Thanks. That makes sense.
Right on. That's a great question, though. Thank you.
Next one is Sashi.
Thank you. Thank you for this wonderful presentation. I have a question which you probably partially answered regarding the power source of the rover. So if we consider a hypothetical situation where we discover some rudimentary life forms or microorganisms, for example, in Mars. So there is a set, is there a set protocol, I guess, so that we don't destroy or contaminate their environment? What could you please throw some light on that protocol? Thank you.
Yeah, thanks for that question. So with respect to this mission, it is not anticipated that we'll encounter any life forms on the surface of Mars, because the surface of Mars is uninhabitable for Earth-like life on a variety of axes, right? It's not just like one axis is really intense. The low humidity is very intense. And so you could envision a super extremophile being able to compensate for that axis of uninhabitability. There are multiple axes of strain on habitability that exist on Mars that make it such that we don't anticipate or expect to encounter any sort of live life on the surface. What you bring up is an important consideration perhaps for future missions on Mars that may be targeted to look more for extant life. And so the way to do that would be to go into the subsurface of Mars via drilling process, most likely, and to be able to get to a level of depth where the radiation environment is sufficiently such that you could expect life forms to still exist. And there will be planetary protection protocols that need to be put in place. And there's a whole office in NASA, the planetary protection, that focuses on exactly this and these kinds of questions that you talk about, where, okay, if we discover life, how do we make sure not to forward contaminate Earth life into those environments such that we don't wipe out any Martian life or extraterrestrial life from their native habitats, right? So there is a whole branch of NASA that is concerned with that. For this mission, it's not really an issue, but for future missions, it very much potentially could be. And then figuring out the exact policy of how that feeds forward into future human and robotic activities on Mars is going to be an important debate at that time. And I think that obviously erring on the side of preserving the natural environment is, in my personal opinion, a very good idea there.
Thank you very much. Thank you.
Thank you.
Next is Martin.
Thank you for the excellent talk and greetings from Kenya. So I have two questions. One is, since there is a finite number of cores that you can collect, are you prioritizing depths of collection, or basically how deep can you collect, or is the different number of sampling sites more important than depth? And the second question is about MOXIE. What are the latest news about it? How successful is it so far? Yes, thank you.
All right, yeah, thanks for those questions. So to address the first one, the most important consideration is the diversity in the sample suites. And that's largely because even with a very small sample, even if, for example, because the sample cores are all the same size, you could potentially envision a scenario where you don't completely fill the core and instead you just get a little chunk of rock in it. But having that little chunk of rock from a diverse set of locations is really important. It's amazing. I mean, you all know this because of the experiments, kinds of environments that you and your colleagues work on, that it is amazing the kinds of measurements that can be made on extremely small phases, whether they're solid, liquid, gaseous, or ionic. And even with the tiniest bit of sample chunk of a rock being left in a core, being able to analyze that in a lab on Earth, you get some very valuable information. Sort of like in some meteorites, not Martian meteorites, but meteorites that come from the asteroid belt, they found proto-solar grains, so grains of kind of dust that predate the sun, so that we're from kind of the pre-solar system environment. And these things are absolutely microscopic. I think they're on the order of, between microns and nanometers for sure, probably closer to nanometers. I'm not sure the exact size. And still, they're able to measure isotopic information out of those and plot them all next to each other and make different groupings of them corresponding potentially to kind of different gas clouds and stellar systems. So it is absolutely incredible what you can do with a very small amount of material. So making sure that we just have material from a lot of different rock samples to do that intensive analysis of is really the bigger consideration, I think, than the actual volume of rock we get in any given sample. But it's a good question. Then the second question is MOXIE. How's it been going? It's gone well. With the runs that they've done, they've successfully produced the amounts of oxygen that they've been expecting. So it works. And then, feeding forward, I think the idea for them, as you can read more on their website, they say it's kind of scale this up with respect to mass and volume to be able to produce levels of oxygen that would then be useful to have for human explorers. Thanks for the questions.
Thank you.
Next one is Marian.
Hi, absolutely amazing talks. Thanks for this. I'll ask a couple of cheeky questions as well about life at NASA. So my first question is about the Mars missions themselves. Like, you have a lot of people continuing from MER through MSL and through to Perseverance, or you have to hire a new crew each time? And then the second question is about JPL itself. I saw that you have an address at JPL. You guys all get private offices, or is it open offices? How's the working environment like?
Nice. Well, thanks for the question. So with respect to the rover team, there are some, it's a mix. So there are some people who've been working since even before the MER rovers that were working on kind of Pathfinder and landers, and have worked on, you know, from there in Pathfinder to the MER rovers to MSL to with Curiosity to Perseverance. And then there are people who are working on Perseverance as their first Mars mission, and we have people on the team who are grad students working as their first mission, people of all career levels working on this as their first mission. So there's a huge range and different levels of experience working on active landed Mars missions, as well as a variety of scientific expertise. So it's nice because it allows for a lot of knowledge transfer there that's super valuable for kind of the younger team members to learn from people who have been more involved with a larger number of these landed missions, and then also for the new people to come in and kind of inject new perspective into it, for people who have perhaps been focused on other topics like the orbital data from Mars, or taking things from more of a modeling perspective. So that's the answer to your first question. Second question, at JPL, you know, it's mixed. I have a shared office, so there's some open work areas too. There's a lot of outdoor spaces. Since it's Southern California, we got pretty regularly nice weather, so you can sit outside and have meetings at the tables and such. And so there's a lot of variability there in you know, shared office, private offices, and meeting in common spaces, meeting outside, meeting in the lab, that sort of thing.
Brilliant. I like the idea of an outdoor office.
Yeah, me too.
There's no smoke, which is a fact.
Yeah, when the fires aren't happening, right?
Yes. So another one by Ashutosh, and then afterwards I will read a few questions from the chat because we have to close soon.
Thank you.
Sounds great.
This is not a cheeky question. It's clear that everything went off extremely well. So if you were to describe the worst loss of functionality, if at all any problem or something occurred or something didn't work exactly as planned, is there a worst case thing that tells us how well everything went, because it's the worst case?
Well, I mean, for me, speaking personally, and I bet that this is also true for a lot of people on the team, the time that my stomach lurched the most during this mission was when we took that image up the sample tube for our first sample and found that it was empty. Because then that was when the engineers who work on the drilling system were scrambling together trying to figure out what happened, and ended up determining that it was an issue with the rock rather than with the drilling system. But obviously that it's an absolutely critical system for the mission itself. And so the fact that it didn't work for the first time was you know, a difficult thing to encounter. But the environment of the team, and I think that this is generally true for NASA, was when an issue like that comes up, it's people aren't laying blame to individuals or you know, fretting about it and just needlessly worrying about it. The attitude is work the problem, right? Figure out what the issue is and what we can do to mitigate it, and what to make it work, what to do to make it work next time. And obviously it showed that whole process worked out, because we've now successfully collected drill core that's inside of the rover's belly, and in the sample collection chamber that will then be returned to Earth. So that was sort of the story of that experience of what we've had so far on the rover mission.
fantastic success. Congratulations to everybody.
Thank you. Thank you. Appreciate it. And I appreciate the question.
Okay. Thank you for the question too. And now I read a few questions which have been accumulating in the chat. I think it's like 3 questions. Adam asks whether there's no problem to fly with the helicopter in the very thin, rarefied atmosphere on Mars.
Yeah, it is very rarefied. That's a good word for that. I might have to use that. So the helicopter was designed to operate within this thin atmosphere, right? The rotor blades move extremely fast and it's extremely lightweight. So it was tested in a chamber where we tried to, or the helicopter team simulated Mars atmospheric conditions and found that they were able to achieve lift and flight and landing. So that's really why this is a key technology demonstration, is to show that you can have a helicopter fly even in that really thin Martian atmosphere, and also go through the whole process of taking off and navigating the terrain and landing. And NASA is pushing forward to do more missions that use this kind of aerial exploration strategy. So for example, the Dragonfly mission has been selected by NASA and is actively being developed and built. And they're sending a multi-copter spacecraft to the surface of Titan, Saturn's moon. And the atmosphere on Titan is substantially thicker than the atmosphere of Mars. I think it's closer to the atmospheric density of Earth, I believe, the atmospheric pressure of Earth, but the gravity is lower than Earth. So you can have kind of a bigger multi-copter than you could have on Earth for the same kind of power source and same blade size. It's maybe closer to somewhere in between swimming and flying in the air, just because of the difference of phase density and gravity and that sort of thing. But for this one, for the thin Martian atmosphere, as you say, we got to keep the spacecraft light and make those rotors move quickly, and that's how the low pressure is mitigated to allow the spacecraft to functionally carry out its tasks. Thanks for the question.
Okay. Next one from Stephen. So Stephen, is the weather easier or harder to forecast than on Earth?
Well, there's a couple of different ways to answer that, right? Because on Earth, we have all of these different weather measurement stations, right? And that's one of the things that makes it easier to forecast, is we have a bunch of data points to feed into the models, which then, given those parameters, they come out with relatively accurate results, right? But on Mars, we don't really have those kinds of weather stations. We have orbiters that are looking up at it from orbit and can sort of measure the broad scale changes in the atmosphere where those orbiters are. But the number of satellites we have orbiting Mars is minuscule in comparison to the number of satellites orbiting Earth making these kinds of measurements. And the number of ground stations is basically just the landed assets that are on the surface, the landed spacecraft, the 2 currently active rovers and the InSight lander. And so that it's really that lack of data of what the conditions are like at the surface of Mars across the globe at any given time that is what makes it substantially harder to forecast the weather on Mars today compared to forecasting the weather on Earth. But in terms of understanding the actual complexity of the Martian weather cycle versus the Earth weather cycle, I'm not sure if you had the exact same number of weather measurement stations measuring the exact same number of relevant variables. I'm not sure which one is sort of fundamentally, from a theoretical standpoint, going to be the more complicated and chaotic system. But for now, what we're bottlenecked by is just the lack of measurements. So hopefully someday in the future that will be mitigated, and we'll also, through missions like Perseverance, have a better understanding of the processes dictating the weather cycle, and coupling those will be able to make accurate weather forecasts for Mars like we do on Earth.
Okay, thank you. Another one by Martin. How do you navigate on Mars? Do you have a GPS?
No, there's no GPS, right? Because GPS is there's a bunch of GPS satellites on Earth. That's what allows us to have GPS. So it's more of a combination of both data from orbiters that give us a sense of what the layout of the land is, and also information that's fed back during the rover drives, right? It has a sense of how far it's gone and the turns it's made. And so you can sort of piece back, like if you were blindfolded and but still recorded the exact distance that you walked and the exact angle that you turned at, and then the exact distance you walked after that turn, you would have a decent sense of where you were relative to where you started, right? And so there's kind of that data being fed into the localization process, but then we also have cameras that take images, and sometimes 3D stereo images that can be used to localize the distance to specific objects. And then we can try and recognize those objects in the high resolution images acquired from orbit, and then know our distance from them. And that also helps us localize where we are. So we got to do it old school style, pre-GPS. But fortunately, the maps are pretty accurate because they're all based on these super high resolution orbital images. So you don't have to deal with having an inaccurate map and also trying to find where you are, like you sometimes need to deal with on Earth.
Okay, thank you. Final question. Rajan asks essentially how the samples get back to Earth, practically, and what is the planned date?
Yeah, so that's still a developing mission. That's actually a joint mission between NASA and the European Space Agency, ESA. And so the actual technology is still being developed, and it's still kind of in just like the planning stages and planning purposes. But the commitment between the two organizations has been pretty good. So you're going to need to get, speaking in broad terms of what needs to happen, you need to get something to land on the surface near where the samples are, right? You need to have something come out of that spacecraft to then collect the samples, like a smaller rover. You then need to load the samples back up into a rocket and launch that off of the surface of Mars. I mean, that's really just the only way you can do it, speaking in broad terms. And then rendezvous with, sort of like in the Apollo missions, where you insert something into orbit around, in that case, the moon, and then lowered, and then a lander flies down and lands on the surface, and then launches again and needs to rendezvous with the orbiter. That's sort of how the Mars sample return would probably work too, where the rocket would launch off the surface, rendezvous with this orbiter in orbit, and then release a payload with smaller mass, so it's easier to accelerate back to Earth, that contains the samples. And then that will be what's sent back to Earth. And the timeline, broadly speaking, is 2030. So we'll see how that develops moving forward.
Okay, this was a very clear answer, and so I think we can close now the session. Thank you very much again for the fantastic talk. I think many people benefited, and it was like 300 people listening, so that's quite a thing. So thank you very much for spending your time, getting up so early for us, and send me your slides, then I can post them.
Sounds good. And thank you very much again for the opportunity to speak to you all. And thanks for all the great questions. All the questions were awesome. So really enjoyed it. Thanks.
Thank you. Bye.
Bye.